Any course questions? Any kind of administrative questions before we start? Yeah.
Just a quick question for the midterm. Since a lot of it is derivations,
Yeah.
you have to write the exam in pen or pencil.
So you are allowed to write the exam in either pen or pencil. Either is fine. There are advantages and disadvantages to either. So if you write in pen, obviously you have to, if you write something wrong, you have to scratch it out. You can just write yourself a new line. That's fine, but you can't erase it. So that's the disadvantage to pen. The disadvantage to pencil is that if you bring us after the test a derivation with a whole bunch of stuff erased and then rewritten and say, look, you marked it wrong, we will be less sympathetic to your case. So there is always if you've written it in pencil, there's always the possibility that you've erased something and rewritten it and tried to pass it off as having been correct. So you get less leeway, not no leeway, but less leeway with remarking in pencil, but you get more flexibility for rewriting it in pencil. Now, the markers are all as good or better at this stuff than I am, so they're very unlikely to make errors in marking your stuff. So perhaps pencil is the better strategy. If I was writing this, I would be writing it in pencil. And if it's clear that nothing has been erased and rewritten, then you'll get exactly as much credibility with pencil as with pen. So, other questions? Questions about the midterm, which is coming up fairly rapidly. OK, good. So let's get into it then. So today we're going to do some derived rules. What do I mean by derived rules? Well, if you've been following in the textbook, you'll notice there's a chunk that we skipped on theorems. A theorem is just a conclusion that you can prove with no premises. So given no premises, you can show a whole bunch of different conclusions. You can derive these conclusions starting from nothing. And hopefully you can imagine how this is possible given what we've introduced so far. If you can't, don't worry. I'm about to derive some before your very eyes. Conjuring theorems as though from thin air. We will do this today. And there are a lot of theorems. Again, if you've been checking the textbook, you'll notice that by the end of chapter 2, there's a list of 125 theorems. These are things that you can get from nothing, which means that at any point in any proof, you could derive these things. Which means that theoretically, you could use any 125 of these theorems as rules. So conceivably, we started off with 4 rules, and then this week we added 6 more. Conceivably, we could add 125 more before the midterm, and then way, way more. We can multiply rules endlessly. I don't want to do that. Let's not do that. We're not going to do that. We're not going to have 125 rules. We're going to pick out a very small number of them that are especially useful and add those in as derived rules. And if you want to use any of the other theorems, I guess remember the proof. You can always use them if you remember the proof. But we're going to add 5 new rules today. And these are all theorems of logic. That is, you can derive them using the rules we've introduced so far. You can derive all 5 of these. And we'll go through a few of the derivations today and just explain them, explain how they might be useful. So this is what we're going to do today, these 5 rules. We'll do them one at a time. So separation of cases. Both of these, are the same rule, basically. These are just the same rule in reverse. Notice that this is the first one we've had that's got 3 inputs. The first separation of cases rule requires 3 things to get triangle out. I hope you can see how triangle comes out of this. The first line, square or circle is true. That first line says one of those things or both of them have to be true. And if you know that one or both of them have to be true, because you've given it as a premise, and you know that if one of them leads to triangle and the other one leads to triangle, then you know triangle. That should be reasonably intuitive. Yeah? And similarly, if you know something leads to triangle, and the opposite of it also leads to triangle, then you've got triangle. Right? Now, you can't using the rules we have so far, you can't get directly there. So separation of cases is not something that you can do in one step currently, but we can do it in a few steps. So I'll show you. But so just again, in natural language, if you know that one of two things is true, and you know that either will lead to the conclusion, you get the conclusion, right? So in the first version, we enforced that one of those two things must be true by saying box or circle. In the second case, you know one of those two things must be true because it's always true that box or not box, P or not P is always true. Yeah? OK, separation of cases. Let's do the derivation for this. So kind of we're just going to practice. This class is largely going to be practice with the rules we have already, showing how they could lead to these derived rules. We're not going to do much of using these derived rules in theorems. But nonetheless, let's try this. So let's do this live. OK. This is theorem 33. So we're going to show this thing on the basis of nothing. So notice the therefore comes first. There is nothing that we're given to show this. Not P, Q, then Q. OK. And what's the major connective here? The then Q. Yeah, so this is the major connective, once again, on the basis of blatant favoritism towards conditionals. So kind of it's if you want to mark it out for yourself what this actually is, you put brackets around it like that. OK. So that means this is a conditional. We can do a conditional derivation. And we get to assume this big thing, pardon me, P or Q, P then Q, and not P then not Q. We're going to assume that for conditional derivation because it's the antecedent. And now we just need to show Q. OK. So we've got a bunch of stuff here. We've got this and we've got that. So let's just simplify that apart for ourselves. P then Q. That's 2. Simplify. 5. We got not P then Q. Again, line 2, simplify. OK. Right. So now what? Now when we're surveying our resources, because we're trying to show a theorem, there's nothing up here. We can't use anything here, right? We've got no premises to draw on. All we've got are available lines. And this available line, this number 2 is an available line, but everything that's available in it is available here or here. So basically all we've got available is line 4 and 5. OK. So now we can use this. To show Q. Oh, I'm sorry. I screwed this up. What did I forget to do? Assume ID. Oh, foolishness. Foolishness. Assume ID. I would have been utterly, utterly stuck there. Right. Not P, then Q. That is to simplify and to simplify. That's why I would prefer to write my midterm in pencil, personally. OK. OK, now we can do some stuff, right? Now we can say line 5 and line 4 modus tollens, giving us not P, and line 4 and line 6 modus tollens, giving us not P, and hooray, we've done it. We've shown on line 7 and 8 a contradiction. We've shown our contradiction. We've shown Q on the assumption that this thing. So line 10, see on line 3, we've done our conditional derivation. Box and cancel. Ta-da! From nothing, we've shown something. Yeah? OK. So, and just take a look. Remember how this is, this is the one version of the separation of cases thing we had, right? So if you have P and Q as a premise, and you have not P and Q as a premise, then you get Q out. Do you see how that's the same reasoning as that rule I just showed you? OK. OK. Do you want to do the other side? Let's do the other side. Sorry, it's cruel to ask you about your desires at 10:22 in the morning. You just want to get through this, I know. So we're going to show this whole thing. And you recognize that this is the same as the other version of separation of cases, right? So if you've got one thing or the other, and you've got both of them leading to R, then you get R. OK. Once again, blatant favoritism for the conditional. So this whole thing is our antecedent, P or Q, and if P, then R, and if Q, then R. We're going to assume that all for conditional derivation. And on that basis, try to show R. OK. Now, we do have this three-part conjunction here. So we recall, where do the brackets go? So this is written in informal notation, isn't it? This is an informal notation. If it was in formal notation, where would the brackets be? They always go to the left, right? Is that right? They always go to the left, right? So the brackets would go here. Somebody correct me if I'm wrong about that. I believe that's right. Yeah, OK, good. Good. OK. So now we've got this two-part thing that we can simplify apart. So if we say if Q, or that's not a Q at all. OK, if Q, then R, that's line 2, simplify. Oh, yeah. Yes, I do. Thank you. Whew. Boy, oh, boy. Right. So now we'll do if Q, then R. We're going to line 2, simplify. And now we can do P or Q. By doing line 2, simplify, simplify. So I've simplified it down to this thing, and then I've simplified it down to this thing. And then P, then R by doing the same thing. Line 2, simplify, simplify. OK. Now we've got a bunch of stuff to work with. Right? All from nothing, by assuming this for conditional derivation, and then remembering, of course, remembering to do assume ID, we've got a bunch of stuff. Yeah?
Sorry, why did you write 2?
Right, the 2 simplify, simplify. So if I do 2 simplify, that's why I was asking about where the brackets go. That's why I was asking, because in official notation, you would add, well, I mean, you'd add another set of brackets out here, but this is a chunk and this is a chunk. Do you see what I mean? So you'd have to simplify. So to get the middle piece or to get this leftmost piece, you need to simplify this whole chunk away from this conjunction and then simplify yourself one half of it or the other. So you need to simplify twice to get there. Yeah?
So if we didn't write that on test, then that would be marked.
Yeah, you'd lose a not a lot of marks, but yeah, that is a small mistake if you don't do that. Yeah.
On logic 2010, do you want us to do like simplify, simplify left, and then right? Like do we have to do this stuff?
So in logic 2010, if you just write S, it'll give you a drop-down menu and ask you which one you want. Or you can do SL or SR for simplify left or simplify right. So either way is fine. If you get it to work in logic 2010, it worked. So, OK, so far so good. And the rest of this proof should be fairly straightforward. So we've got not R. Using not R and P or Q, we can say line 4 and line 6, modus tollendo ponens. And that gives us, because this is the negation of, no, it's not. No, it's not. It should be straightforward. It really should. Okay, so let's do it the other way. So let's do 4 and 5 modus tollens, giving us not Q. Now we've got the negation of part of this. So if you've got not Q and you've got P or Q, that means P must be true. So that was line 6 and line 8, modus tollendo ponens. Okay? And now we've got if P then R, so 7 and 9, modus ponens, giving us R. And now we've got our contradiction. Line 4 and line 10 contradict each other. So 4, 10, ID. Box. Cancel. Yeah? And on line 12, because we've shown R on the assumption that this thing, we've done on line 3 our conditional derivation. Okay? I'm going a bit faster now. I hope that's okay. You will face time constraints on the test, so speed is a factor in how well you do on this task. I'm going to start ramping up the pace at which I'm doing these derivations. So, okay, any questions about that? Yeah, yeah.
If we get not Q and not P, can we say it's a contradiction with line 6?
If you get not Q and not P?
Yeah.
Well, if you've gotten not P, you could have generated Q. So you can't say, if you've got not P and not Q, there's no, that would be 3 lines to do your ID. You want just 2 lines to do your ID. So, but if you had not Q, then what you could say is, I know not Q is true, so I know P is true. And if you had not P, then you've got P and not P as your contradiction. Is that okay? Yeah. Yeah. Okay. So that's separation of cases. Those are the proofs for the 2 halves of that rule. So that's that and that. Okay? Separation of cases. If I'm going to be honest with you, this is not one of the more useful rules. I don't find this one coming up in derivations all that often. But now you've got it. Okay. Negation of conditional. This one is a useful rule. I mean, they're all fairly useful, but this one's more useful than separation of cases. If you've got the negation of box then circle, then you've got box and not circle. And if you've got box and not circle, you can get the negation of that conditional. This is really useful if you've got a conditional that you're trying to show. Here's just another way, and your conditional derivation isn't working. Here's another way of deriving the conditional. So you assume ID on your conditional, and then you can turn it into these 2 things, and then you can generate your contradiction. Okay. So. I'll do the derivation as well, but I thought it might be helpful to start layering in some of these truth tables as a way of convincing you that these things are logically equivalent. So the point of this diagram is to try to show you that this column, not if P then Q, is logically equivalent to this column, P and not Q. Right? So what I've done here is just assign truth values to P and Q. So this says P is true, P is true, P is false, P is false. Q is true, Q is false, Q is true, Q is false. And then we just see what happens in each of those cases. So if P is true and Q is true, then if P then Q is true. So this part is just the truth table for the conditional, right? So that all looks good. No errors there. Now this line, you just negate this. So whenever this is true, this is false. And whenever this is false, this is true. Right? So far, so good? Yeah? And then not Q is, of course, just the negation of this. So whenever this is true, this is false. So false, true, true. Yeah? And then P and not Q is true whenever both not Q and P are true. So P is true and not Q is false, it's false. P is true, not Q is true, it's true, and false otherwise. So the logical equivalent comes out of the fact that these ones are all the same as these ones. Yeah? That's what logical equivalence means, is that for all assignments of truth values, all of the possible ways of assigning truth values, if two things come out the same, then they are equivalent. They are logically equivalent. Yeah? And that's what all these rules are showing, is that if you have the truth of one thing, you're guaranteed to have the truth of the other. And if you have the falsity of one thing, you're guaranteed to have the falsity of the other. Yeah? OK. Oh boy. So let's try and derive this. All right. For practice doing derivations. All right. I'm going to show P and not Q. Then, oh, sorry. I'm just going to do, for the sake of time, since we're already 20 minutes in, I'm just going to do 1/2 of this biconditional, if that's OK. So this is theorem 42, showing one side of this. We could also do theorem 40, which is the biconditional version of it, but it's twice as long. So I'm just going to do 1/2, if that's all right, for the sake of brevity. Yeah? OK. OK. So let's show this thing. Once again, oh, there's a huge mess of symbols here. It's a huge mess of symbols. But blatant favoritism tells us that this is the main connective. So we got this thing and this thing, right? So we're going to assume the antecedent, P and not Q. Assume that for conditional derivation. And try to show that it's not the case that if P, then Q. OK. This time, I'm going to remember to assume ID, because it looks like it's going to be useful to me, right? If P, then Q. I'm going to assume that for indirect derivation and try to derive a contradiction somehow. So fairly straightforward, I hope, I think. Line 2, simplify, gives us P. And then 4 and 5, just an obvious automatic move. 4, 5, modus ponens gives us Q. And then we got our contradiction, right? There's a contradiction lurking if we just use the other half of this. So once again, premise 2, simplify, we get not Q. And that's it. 6, 7, ID. And then on line 3, we've done our CD. Ta-da! Do this final, doing this final cancel and box thing, like, when you're doing a subderivation, it makes total sense why you're doing this. You're boxing it off to show yourself visually that you're not allowed to use this stuff anymore. And you cancel the show line because you're no longer trying to show it. Now you have this thing. That's what you're saying here, is I'm not trying to show not P then Q. I have not P then Q, and you can use it. The practical reasons for doing this last cancel and box are less clear to me. I think it's just kind of like a magical ritual that we do. Like, it's kind of like, it makes it feel complete in some sense. It's got a ritual quality, I feel. Anyway, OK, is that derivation straightforward? Good, good. OK, so you can see there's 2 halves of this thing. I'm just going to do 1/2 of it, just for brevity. OK, another one. So this is our 3rd derived rule. De Morgan's. De Morgan's is great. De Morgan's is my favorite derived rule. It's weird for me to, I feel weird having a favorite derived rule, but it is nonetheless my favorite derived rule. Unfortunately, the catch with De Morgan's is it comes with a bunch of different versions. So I can tell you this very clear sentence. the negation of a disjunction is equivalent to the conjunction of the negation of its parts. And of course, the negation of a conjunction is equivalent to the disjunction of the negation of its parts. That should be super clear and easy, right? OK, let me just show you visually. OK, so De Morgan's has 8 versions, but they all do basically the same thing. They all do basically the following. They take the negation of either an and or an or statement and just kind of flip it. So you say, if you have the negation of and, you get it's not the case that one thing, or it's not the case that the other. And of course, backwards. If you can infer one from the other, then you can infer the second thing from the first. And if you've got the negation of a disjunction, if you've got the negation of an or sentence, then you get not the first thing and not the second thing. So this is something suddenly the negation of and or statements have become super useful to us because you can crack them open. Before, the major connective of this sentence, this not and not square and circle, is this negation. And there's not all that much you can do with a negation. We don't have all that many rules to apply to it. We've got double negation. That's fun. You can try to use it to derive a contradiction. That's fine. But you can't use the juicy insides of this thing, right? It's locked inside the negation. But using De Morgan's, you can crack it open, and now you have access to the parts. Yeah? So this is really, really useful. OK? But there's also, so here's another 4 versions of De Morgan's. These are all called De Morgan's. So if you have square and circle, then you can get, it's not the case that not square and or not circle. And if you got square or circle, you can get it's not the case that not square and not circle. These are less, I mean, I use these versions of this less. It's fairly rare in my experience to need to get. It's not the case that not box or not circle. It's very common that you've got the negation of a conjunction or a disjunction, and you want to get something useful out of it. But nonetheless, these are all available to you as moves now. OK. All right, so once again, let's do this truth table style, try to convince ourselves that these all make sense. So got just random. So these are just assignments of truth values to P and Q. So given this assignment, how does it work out on all these other lines? This is just the truth table for and. That should be fine. This is just the flip side of the truth table for and. So if it's true that not P and Q, that it's false if P or Q are true and true in any other case. Just the exact opposite of the conjunction truth table. So far, so good? That should jump out at you, scream at you with obviousness. OK, and then the truth table for not P and not Q are just the opposite of the truth tables for P and Q. And then this is just whenever this is true whenever one half or the other is true. So in the first row, they're both false, so it's false. And in all 3 other rows, at least one of them is true, so the whole thing comes out as true. OK? So now we look and see, OK, is this logically equivalent to this? Is not P and Q logically equivalent to not P or not Q? And yeah, they're the same on every line. So for any assignment of truth values to P and Q, these 2 sentences come out with the same truth value. OK? OK. Yeah?
Will we have to show truth tables on the midterm?
Yeah. So we haven't learned how to do these yet. I have not yet taught you how to do truth tables. We're going to do them next week. So just a reminder, there's no class on Monday. Be thankful. And then on Wednesday, we'll do truth tables. But I thought, given that I've been showing you the truth tables for the connectives, I thought this would be intuitive enough that you'd be able to recognize what's going on here. Is that fair? Or are you just baffled by what's going on here? What are all these T's and F's? This is actually a serious question. I don't know whether this is helpful or not. This is, for my money, this is a much faster and easier way to convince myself that these two things are logically equivalent than doing the derivation. But, okay, I'm just going to leave this in the slides for you to, if you want to convince yourself that the other half is true, you can just investigate this table. Yeah. Do you want to do more? Oh, like, do you want to do this derivation? Is that? Oh, let's do the derivation. Why not? All right. So there are at least 3 De Morgan's derivations. There are 4 De Morgan's derivations, but let's just do this one. Okay. Is this the right one? Yeah. Yeah. Okay. Okay. We're going to show P and Q biconditional. Not the case that not P or not Q. Okay. So we're trying to show a biconditional. What do you do when you're trying to show a biconditional? We talked about this last time. You want to do, this is the plan. First you're going to show one direction, and then you're going to show the other direction, and then you're going to conditional to biconditional them together. Okay? So this is our plan for this derivation. Okay, so first we're going to show if P and Q, then not P or not Q. And that's just a good old-fashioned conditional derivation. So we're going to assume this for conditional derivation and show that not P or not Q follows. Oh, that was badly rendered, I'm sorry. Not Q. Okay. And we'll assume the opposite for indirect derivation. Okay. So we've got 2 available lines. We're doing a theorem. We've got no premises to work with. We've got 2 and only 2 available lines. We got P and Q and not P or not Q. So I'm supposed to do 3 simplify. So I'm simplifying myself off P, and we'll double negate it to get not P, and then modus tollendo ponens. Do you want me to do every step of that to see it, or is that all right? Okay. Anybody? Okay. So actually, I'll just do every step. So 3, simplify, you get P. 5, double negate, you get not P. That's not a D, that's a P. And then not P and 5, so we get, screwed up the line numbers. Sorry, 7, 8. So on 5 and line 7, we've got modus tollendo ponens. So that gives us not Q. So the negation of one half of a disjunction gives you the other half. Okay, so we've got not Q. All right, cool. What else have we got to work with? Yeah?
Line 3, Q?
Yeah, that's right. That's right. So on line 3, we're going to simplify and give ourselves Q. Great. Got Q and we got not Q. So on line 8 and line 9, we've done an indirect derivation. Box and cancel. So on the assumption, on the assume ID of this thing, we've shown a contradiction, therefore the negation of it must be true. And then on line 4, we've done our conditional derivation. Okay, good. So that was this half of that, right? We showed one direction of the biconditional. Yeah?
For step 5, when you're doing the indirect derivation, you have to show the double negative as well.
Not when you're doing assume ID. Yeah. Sorry, I recognize that I'm being mildly inconsistent about that across rules, but so is Logic 2010. So, okay, so now we just have to show the other half, right? We're going to show if not not P or not Q, then P and Q. Okay? And then we'll assume not P or not Q for conditional derivation. Try to show on that basis P and Q. And just because I've forgotten so many times today, we might as well assume this thing for indirect derivation. Why not? If you had De Morgan's, this would be a super useful line. We're currently trying to show De Morgan's, so we're not allowed to use it on this in this proof. But if you had De Morgan's, you could crack this open, right? You could get not P or not Q. But OK. Basically, it would be nice to show P and Q, or like show P, show Q. Or we could do the opposite. All right. So what now? Okay, I'm gonna scroll up on the basis that this is all boxed off, and I don't currently have the antecedent of this, so there's not much I can do with this. So I'll just scroll up. Well, we're proving De Morgan's at the moment, so we're not allowed to use it yet. Yeah. OK. So I don't know about you. I'm feeling stuck. Are you feeling stuck? I'm feeling stuck. What do we do when we're stuck? We write a show line. Right, so we're going to try to show something. Now, of the options that we've got, like, there isn't much to work with here. So we've already got show this. So we've already got a show line for this. So showing this isn't really good. So we're going to try to show the contradiction of something, right? We're going to try to show something. In this case, because we don't have a nice conditional to work with, really the only thing to show is something that's the contradiction of something that we've got. And we've really only got one thing here. We've really only got this. Right? That's basically the only available line that we've got that's going to be useful. So I'm going to write a show line for this, the opposite of this. So show not P or not Q. Yeah? My God. Right. Am I stuck here? I'm absolutely stuck here. Yeah.
For conditional derivation, can we assume the right part is not true and then show the antecedent is not true as well?
Well, that's basically what we've done. So the question is, can we, for conditional derivation, can you do like a modus tollens on it? Notice that what we've done here is assume that for indirect derivation that the consequent is false. Yeah?
So can we just assume the consequence is false then?
No, you got to do it this way. You got to do it this way. Yeah. Oh man, I thought I'd be able to do this on the fly. Yeah.
Would it be possible to show P?
Very good.
If you show P and you ask the idea, you would get not P, and then the rule add, you can add anything to the other side. So
Very good.
I did not Q
Okay.
13 ID.
Good. So show P. So actually, do you want to do that instead of this line?
Yeah, instead of the show.
Okay. Let's try it. Show P. And then give ourselves not P for assume ID. OK. So we've assumed not P. And then what he said was, look, given not P, can I get this thing? Yeah, I can. I can just say not P or not Q. by using line 17, add. Thank you. I was sweating trying to figure out how to get through this. And that was the right answer. That is the right answer. Because now, look what we've got. Line 13 and line 18 are the negation of each other. Oh, thank God. OK. So 13 repeat and line 18 are indirect derivations. So we've shown P. Whew. OK. Now, look what we can do. So we've shown P. Now we can use the exact same strategy to show Q. There's nothing that we have for P that we didn't have for Q. So now we just say show Q and do the exact same thing. So not Q for assume ID. 22. So now we can say not P or not Q by adding. So say line 21, add 23. That's our indirect derivation again. So line 13, repeat it into the subderivation. Line 22, ID. So now we've shown P, and we've shown Q, meaning we've got P and Q from line 16, 20, adjoin. Hooray! And that's a direct derivation of the thing that we're trying to get. Yeah? OK. Thank you very much, by the way. I did this on Logic 2010 last night, and I wrote it out by hand last night, and then I forgot how to solve it. OK? OK. Whew. But now we're getting there. We're getting there. Look, so on line 14, we showed the thing that we were trying to show for our conditional derivation. So line 14, we did a conditional derivation. Box, cancel. And now, we've done both sides of this thing. We've done the other half. Ta-da! Now we just conditional to biconditional them together, and we're done. So line 2 and line 12. Yeah. 6, line 2, line 12, conditional to biconditional. So that means we've got if P and Q, biconditional, not P or not Q. And that is our direct derivation. Ta-da! OK. There's that. OK, we're running out of time, so I'll just leave it there if that's OK. OK. So, De Morgan's. Conditional as disjunction. I'm not going to derive this one. I'm not going to derive this one. The derivations get longer and longer from here on in. Conditional as disjunction. If you've got a conditional, you get this disjunction, which kind of helps to make sense of how the conditional works. So if I say, if I'm a reptile, then I smell great. And that's true. That's actually true. Well, assuming that I smell great. No, it's true in the real world. Even though I'm kind of sweaty from having panicked on that derivation, I don't smell all that great. But I'm not a reptile. I can guarantee that. So it's true that if I'm a reptile, then I smell great, because what it's actually saying is either not the first thing or the second thing. Yeah? OK. Super useful if you need to show a disjunction. If you're asked to show a disjunction, what you do is just write yourself a show line for not P then Q, and then do a conditional derivation, and then CDJ back to the disjunction. OK? Sorry, I'm going to have to zoom through this because I spent too much time on those derivations. Once again, you can convince yourself. Look at this table. If you're not convinced that these are logically equivalent, look at this table and convince yourself. One last rule, negation of biconditional. So if you have the negation of the biconditional, you can get the negation of, so biconditional negation the other thing. Okay? Okay. Again, look at this, convince yourself if you're unconvinced. You're going to have to convince yourself in a more thorough way, however. So the caveat is, to use these rules in Logic 2010, you have to prove the relevant theorems. Logic 2010 is set to show to use. So you're going to have to show these things. And I want you to try to do this. So this is extra homework for this week. Try to show these things. You don't need any of these rules to get through to this week's exercises. So you don't have to do this week. But sometime next week, I'm going to give you exercises where you do have to use these rules. So you're going to have to prove all these theorems. Now, I do not want to ruin your life. So what I've done is the following. On Quarkus, at the bottom of this homepage, we've got derived rules theorems. And you'll see, so here are the theorems you have to prove. And I would like you to try to prove them on your own. This is really good practice. If you get utterly, miserably, horribly stuck, then I've given you the answers. I've just given you the answers. So you click on this, and here's the answer. So this is why I didn't derive the negation of biconditional in class. Here's the derivation for negation of biconditional. It's 53 lines long. You are not going to be tested. I'm not going to ask you to prove this on the test. You notice there are fewer lines in the sheets that I gave you than are in this conditional, or in this derivation. So I want you to have gone through these proofs. So at minimum, print this out and just type in the answer. But it would be better if you derive them yourself. OK? OK, that's it for today.